All right. What problem or problems would you guys like to look at? Anybody at all? From number 1?
Yeah.
Yeah, of course. All right, so we're asked to factor this polynomial given that x plus 4 is a factor. So what we'll do is we'll start by dividing that polynomial by x plus 4. Since x plus 4 is degree 1 with leading coefficient of 1, we can do that using synthetic division. So we'll set x plus 4 equal to 0 and solve. That gives me negative 4, which I put on the outside. And then I'll take the coefficients of that polynomial and put those numbers on the inside. And when I do my synthetic division, I get remainder 0, as I would hope. Now, when I combine this together, I know x plus 4 is one of my factors. And then this information at the bottom gives me my other factor. So remember, this is the constant term, the x coefficient, and the x squared coefficient. Then I'd want to check to see if x squared plus x plus 1 can factor anymore. So I look at this and I notice it's in the quadratic form. In fact, it's not just in the quadratic form, it's like expressly quadratic. Okay, so if this can factor, I would need to look at whether I can do the short or long factoring. Since the leading coefficient on that polynomial is 1, I should be able to factor doing the short factoring. So all I need to do is look for a number that multiplies to give me 1 and adds to give me 1. Are there two numbers that multiply to give us 1 and add to give us 1? They're not integers, right? 1 times 1 is 1, but 1 plus 1 is 2, right? So that doesn't work. In fact, there's not a pair of integers that is going to satisfy that. So we're done factoring this. That's as far as it can go. That quadratic piece this time couldn't factor anymore. Okay with that so far, Alyssa? Yes. Okay. So if we go down to number 2, and we want to try to solve this, we can just set each of these two pieces equal to 0. So the first factor gives us a solution of negative 4. What do I get, or how do I solve x squared plus x plus 1 equal to 0? I use the quadratic formula. Since I know I can't factor this, I just established previously that this can't be solved by factoring, I'll use the quadratic formula. So x equals negative b plus or minus square root b squared minus 4ac all over 2 times a. So that's going to give me negative 1 plus or minus the square root of negative 3 all over 2. And the one thing I have to worry about there is the square root of a negative. Remember, that creates an imaginary number. So I'll replace the negative 1 underneath the square root with an I in front of the square root. So the rest of my solutions are there. Is that okay, Alyssa?
Yeah.
So again, just because we do that synthetic division and you get another polynomial back that's not degree 1, doesn't necessarily mean that other polynomial is going to be factorable, right? It could be something that is prime that doesn't factor, at least factor over the integers like we're trying to factor. So we do need to be a little bit careful there. Okay? Who else has one that we want to talk about? Anybody else? Julia? Yeah, of course. So just like C, I'm going to start by doing the synthetic division. So I'm going to divide this polynomial by x plus 3. So when I set x plus 3 equal to 0 and solve, I get negative 3. And then I'm going to use the polynomial to put the numbers inside my synthetic division bar, but I have to be a little bit careful here. Notice in this polynomial, I go from x cubed to just regular x. I skipped the degree 2 terms, so I need to make sure I include a 0 in the spot where the x squared terms would be. So when I do the synthetic division, I get remainder 0, as I would expect. So that's going to give me x plus 3, and then x squared minus 3x minus 10. I should then check to see if I can factor x squared minus 3x minus 10. I notice that's 3 terms. It's in the quadratic form. Its leading coefficient is 1. So I just need to find 2 numbers that multiply to give me negative 10 and add to give me negative 3. Are there 2 numbers that do that? Multiply to give me negative 10 and add to give me negative 3. Zach, you said 2 and negative 5. That is correct. And so my fully factored form then would be x plus 3, x plus 2, and x minus 5. Julie, are you okay with that? So the common mistake probably would have been forgetting to include the 0. Got to be careful about that. I picked this problem in particular because it required to have a 0 in there. And I was assuming that between the end of last semester and the start of this one, some of us forgot about that little catch when doing the synthetic division, which is why I created this problem to remind us about that. So it was good. I'm glad you asked about it. It was an important detail that's easy to kind of forget about. Okay. And then obviously the solving from here is easy once it's in this factored form, right, Julia? Yeah. So negative 3, negative 2, and positive 5 would be your 3 solutions there. Okay. Anyone else? 1D. Okay. So we'll start just like we had for the other ones. So I'm going to have 1 out here and then 1, 1, 7, 9. We'll bring that first number down. Oh, I forgot the negative 18 at the end. So 1 times 1 is 1, and then I get 2. 1 times 2 is 2. That gives me 9. 1 times 9 is 9. That gives me 18. 1 times 18 is 18. That gives me 0. So I'm going to have x minus 1 times x cubed plus 2x squared plus 9x plus 18. And now I should check to see if I can factor that polynomial. So that has 4 terms. So if I go back to my factoring tree, I would want to try grouping on this polynomial. So I'll try making 2 groups. From the first group, I can take out an x squared. From the second group, I can take out a positive 9. And I notice then that each of those has an x plus 2 in it. So if I factor out the x plus 2, I'm left with x squared plus 9. And I should check to see if I can factor the x squared plus 9. I can't, right? It's not a difference of 2 squares. That's a sum, and sum of 2 squares aren't factorable. So this is as good as I can do. And then in part 2, to solve this, I would get 1, negative 2, and then plus or minus 3i as my solutions. I know you didn't ask about part 2 for this, but I figured we did all the hard part. I can at least give you the answers. If anybody had questions on that, that might have sparked some, but should have been pretty easy solving at that point. The factoring is the hard part, right? Once we get past the factored, or get the factoring done, it's usually pretty easy to deal with from there. Julia, you got a question? I know I see you pointing at stuff. You're good? Okay. If you change your mind, let me know. Okay. I'm just trying to be responsive, you know? Okay. So let's kind of move forward here. All right. So notice on these problems that we worked on, in each of them, I gave you some information about one of the factors, right? What we're going to deal with today is what happens when I take that information away. So let's look at an example here. What if I ask you to factor something like, let's not do that. 2x to the third plus 7x squared minus 3x minus 18. Now notice here I don't give you a factor to use to start doing our synthetic division, right? If you look at this for a moment, you'll see quickly that it's not going to be factorable by grouping. So we're going to have to figure out a factor to use to do the division on our own. Okay, so you want to see that real quick? Well, let me finish writing this sentence and I'll do a little aside and then we'll come back and we'll do that. Okay. So just as an aside, Zach says, why is this not factorable by grouping? And that's a fair question. So let's say we try and we make two groups. Notice that I wrote it as plus a negative instead of the subtraction symbol there. From the first group, we can take out an x squared. And from the second group, I can take out a negative 3. The reason it's not factorable by grouping is when I do that, I don't have any common factor left over afterwards, right? One of them is 2x plus 7, the other is x plus 6. In order for me to finish the factor by grouping, those two factors have to be the same. Does that make sense? And if you know what you're looking for, it's not hard to see that from the beginning, right? But that's a good question, important that you asked. Clayton? Of course. Okay. So we know we can't do the grouping to do this, so we're going to have to find a factor to use to get this division process going. How many choices would I have of possible factors? I say I have to find one. Well, how many am I have to pick from? How many possible factors could this have? Could x plus 1 be a factor? Sure. How about x plus 2? X plus 3? X plus 4? Yeah, right? How many possible factors could this have? Infinitely many, right? That's bad. That's a lot of things to have to possibly check, right? So we'd like to do better than that, right? Trying to check infinitely many things. If you're guessing from an infinite many list, pretty hard to guess correctly. Everybody okay with that idea? So we want to do better than that. And we can. So over the next, week or so, we're going to be working on ways to do a better job of picking kind of the things to start with, what to use to do these synthetic divisions. That's going to be kind of the process. Okay? So we're going to do that using a bunch of theorems. So we're going to see a bunch of theorems over the next week or so that are going to be our tools that we're going to use to kind of do the synthetic division process and use it to kind of streamline that process and make it a little bit more effective. So the first theorem is called the rational roots theorem. And before I describe this, I just want to point out to you what we mean by a root, because this is a piece of vocabulary that I didn't mention last time. So a root is just, they are the values that make a polynomial evaluate to 0. So they're basically just solutions to the polynomial equation, right? It's basically the same thing. I mean, the definition is technically like a little bit different, but like not so much as it's going to cause any problems for us. So you can just think about them really kind of the same thing as the solutions, which are indeed really the same things as the factors and the x-intercepts and the zeros. They're all kind of the same number. They all tell you the same information. Okay. So what the rational roots theorem says is for a polynomial with integer coefficients, the possible rational roots are of the form plus or minus factors of the constant term divided by factors of the leading coefficient. Yep, possible rational roots is what that says. When I say the word rational, what do I mean there? We mean something like a rational number. So things that are fractions or can be written as fractions. So whole numbers or fractions, basically. Form. So maybe in reading this, it's not entirely clear what this is really saying or how this is going to be useful to us. So let's look at an example. Okay with that? So let's find the possible rational roots for this polynomial we were just looking at a second ago. So this is the same polynomial we were just looking at. And we're going to just use it as an example of applying the rational roots theorem. So there's two things that we care about for the rational roots theorem. We care about the constant term, and we care about the leading coefficient. What's the constant term in this polynomial? Negative 18. Okay. And what's the leading coefficient in this polynomial? What's our leading coefficient here? It's 2, right? This guy's the leading coefficient, and this guy's the constant term. Everybody's okay there? You remember that vocab from last semester now? Okay. So what I need to do then is I'm going to look at factors of negative 18. And when I write factors of negative 18, I really only care about the positive factors. The negative ones will pick up because of the plus or minus here later on, so I don't have to really worry about those. I'm just going to worry about the positive numbers that divide 18. So what are the positive numbers that divide 18? What? Somebody said something. 6 and 3. Great. Those are both numbers that divide 18. What else? 1 and 18. Cool. And 9 and 2. Great. Are there any others? No, that's all of them. Okay. Now we're going to look at the factors of the leading coefficient. So what are the factors of 2? 1 and 2. Everybody agree there? Okay. So according to the rational roots theorem, my possible rational roots are going to be a factor, or the positive or negative of a factor of the constant term divided by a factor of the leading coefficient. So I could have plus or minus 6 over 1. I could have plus or minus 3 over 1. Plus or minus 1 over 1. Plus or minus 18 over 1. Plus or minus 19 or 9 over 1. And then plus or minus 2 over 1. And I could also have plus or minus 6 over 2. Plus or minus 3 over 2. Plus or minus 1 over 2. Plus or minus 18 over 2. Plus or minus 9 over 2. And then plus or minus 2 over 2. Everybody okay with how I generated this list? Now there's a little bit of duplicates on this list. I've listed the same number here more than once. What does 6 over 2 reduce to? 3. And I have 3 listed already here, so I'm just going to put an X through that because I don't want to list these things more than once. What other duplicate do you see? 1, right? 2 over 2 and 1 are the same thing, so I'll cross that out. And there's one more duplicate. 18 over 2 is the same thing as 9, which is also already on my list, so I'm going to cross that out. So, how many possible rational roots do I see here? You said 9. Be careful because each one of them is positive or negative. So there's really 18. Okay? So these rational roots are equivalent to factors. So going from infinitely many factors that are possible, I've gone down to 18 of them. That's not bad, right? We certainly took a big chunk out of the possible guesses that we have to make. So let's now try to factor this guy using this list that we just wrote up. So let's pick one of the values from this list and try using it. There's really no way to know which ones would work or wouldn't work, so we're just purely guessing. So let's just make a guess. So the first one is, you want positive 6 or negative 6? Positive 6, okay. So I bring that, the 2 down. So 12, 19, 6 times 19 is 114. So 111, so that's 666. Ugh, that's scary. And I get 648. Did that work? No. What was I supposed to get as that last number? 0. So 6 doesn't work. Okay? Let's pick another one. Negative 6. Okay? Uh, 120, 162, I think. So that's what, 180? Did that work? No. Okay. On to the next one. 1. All right. Nope. -1, okay. Nope. There's only 12 choices left, I think, right? We've done 6 of them. Oh, we've only done 4. There's 14 still left. 3, okay. Uh, 39, 36, that's what, 108? Nope. -3, this is a good guess. All right. So what does this tell us that we get? How can we factor that polynomial now? We get an x plus 3. That's because I got a remainder 0 when I divided with -3. Okay? And then what else do I get? Very good. So this stuff then gives me my other polynomial. Everybody's okay there? Now I have some options here. I can try to factor 2x squared plus x minus 6, or I can continue dividing this stuff with numbers from my list. Doesn't really matter which one you do. Either is okay. What would you like to do? Try factoring the 2x squared plus x minus 6 by hand, or continue dividing, just guessing at things from our list? Factor it by hand, okay. So this has 3 terms. It's in the quadratic form. Its leading coefficient is not 1, so we'd have to do the long factoring on this. So I'm going to need the 2 numbers that multiply to give me the leading coefficient times the constant term, and then add to give me the coefficient of the middle term. What are the 2 numbers that multiply to give me -12 and add to give me +1? There are 2 numbers that do this. Multiplies to give me -12 and adds to give me a +1. 4 and -3 is what Zach says. That is the 2 numbers that do that. Now, unfortunately, these 2 numbers don't take me straight to my answer. What they tell me is how to break up that polynomial so I can factor it by grouping. So the x plus 3 comes down still. And then I'm going to rewrite 2x squared plus x minus 6 as 2x squared plus 4x plus -3x minus 6. And then I'll make my 2 groups. From the first group, I can take out a 2x. From the second group, I can take out a -3. Notice here that the x plus 2's are also in common. So if I factor out the x plus 2's, I'm left with just the 2x minus 3. So there is my factored form. What's the drawback to what we're doing right now? To what we just did for this problem? What made it kind of annoying? Yeah, we had a lot of wrong guesses, right? What if I told you there's a way to eliminate a lot of the bad guesses? Would be nice, right? So I am telling you there is a way that exists that you are perfectly capable of coming up with that allow you to pick the stuff that is probably almost certainly going to work from your list. Anybody have an idea of how I might do that? Let me give you a little bit of a hint. If I go back to yesterday, this is where I want to be living. So what we're looking for is factors, right? Everybody agree with that? We're having trouble finding them. What I'm telling you is that, okay, if we're having trouble finding the factors, maybe I can find one of these things easier. So would it be easier to find solutions, x-intercepts, or zeros? What would be the easier thing to look for? What thing can we do easily? It's the x-intercepts. That's exactly right. Why can we get how can we get the x-intercepts easily? We can graph it on the calculator. And that's exactly what we're going to do. So, what the plan is going to be is before we start picking or making these guesses all willy-nilly, I'm going to graph this on the calculator. I'm going to look at the picture and identify the x-intercepts. I'm then going to go to my list and pick the things from my list that match the x-intercepts that I see on my calculator. And those are the guesses I'm going to start with. More often than not, it's going to eliminate wrong guesses. Almost always you're going to get something that works. So you can eliminate a lot of the guessing. That's a pretty good deal now, right? We went from infinitely many guesses to a finite number of guesses, but maybe still kind of a lot, down to, okay, from that finite list of guesses, I know which ones are the good ones to try. That's a pretty good deal, right? I'd be pretty happy. I'm pretty happy with that. You know? Maybe not. You're not happy? I think that's a good deal. So let's illustrate this. All right, so I'm going to fire up my calculator. Again, if you have your graphing calculator with you and you'd like to follow along, I invite you to do so. Ty. Of course. Well, I kind of run through exactly what I'm doing here. But this is mostly just, you got to get a decent picture out of your calculator and then look at the picture. It's not much more to it than that. Okay? So, if I want to look at graphs on my calculator, the first thing I'm going to press is the y equals button that's in the upper left-hand corner. And for that y equals button, I'm going to clear out whatever's in there. And I'm going to type in the polynomial that I'm interested in factoring exactly as it's written on my sheet of paper. Is everybody okay there? Okay. So what I'm going to do next, before I graph this, is I'm going to pick a window in order to graph this on. So I'm going to press the window button, which is right next to the y equals. And now I want to make sure that when I graph this thing, I'm able to see whatever, or see any of these if they might be actual x-intercepts that I care about. So what I need to do is identify the smallest and largest x-intercepts on this list. What's the smallest possible x-intercept from this list? The smallest number on that list. Well, there's a number much smaller than 1/2 on this list. -18. Remember that these all have plus or minuses in front of them. The smallest one is -18. What's the biggest number on this list then? +18. Okay? So what I'm going to do for the x min is I'm going to pick something a little bit smaller than -18. So -20 would be fine. And for the x max, I'm going to pick something a little bit bigger than +18. Well, positive 20 seems fine. Now, the y-mins and y-max don't really matter. I just want to make sure that the y-min is a negative number and the y-max is a positive number because I need to see the x-axis. If both of them are negative or both are positive, I wouldn't be able to see the x-axis. And that's really all I care about here. I don't care about what the rest of the graph is doing. I just want to see where it's crossing the x-axis. So I'll use negative 10 and positive 10 for my y-min and y-max. And I really probably never change that. Everybody okay? All right. So let's hit graph and take a look at what we get here. All right. So I see the graph crosses 3 times, but it's probably too far away for me to be able to really read those tick marks. So I'm going to go back in and adjust my window. So let's think about looking at the picture here, what I would want to adjust it to. So this is like negative 20 out here. So like halfway in would be like negative 10. And then half of that seems like negative 5. And that seems like probably a good place to go to. Everybody kind of agree with that? It doesn't have to be precise. You just want to make sure you get everything on the left side of the graph. All the x-intercepts on the left side of the graph will still be in your picture. If I look at the right-hand side, then this is 20. So that's like 10. That's like 5. That's good, right? I can still see all the x-intercepts on the positive side would all be captured there. So I'm going to pick negative 5 to positive 5. Again, when we do this adjusting where we zoom in a little, it really doesn't matter what you pick. You just want to make sure you can still see all the x-intercepts you could before. So if I could see 3 x-intercepts on the biggest picture, when I zoom in, I just want to make sure I can still see all 3 of them. It almost doesn't matter what you pick. You just want to be able to get close enough to where you can count on the x-axis, the tick marks, and you can see all the x-intercepts. So there's not really any rhyme or reason for the numbers I picked. I just kind of estimated. Okay, so I'll hit graph again. Okay, so you see, I know it's hard to see on the projection, but there are little tick marks here. So if I start at 0, this tick mark would be negative 1. This tick mark would be negative 2. This one would be negative 3. So 2 of the good places to start would be negative 2 and negative 3. If I look at the positive side, this is positive 1. This is positive 2. So what does the x-intercept look like? 1.5 maybe? So if I went to my graph first, I would have liked negative 2, negative 3, and positive 1.5. So if I go to my list, well, I have negative 3 here. I have negative 2 there. And I have positive 1.5 there. Any one of these 3 would have probably been good places to start. And in fact, when we actually got this to work, guessing, we did use negative 3. So we could have shortcutted past all of those wrong guesses by looking at the graph on our calculator before we started the synthetic division. Is everybody okay with that idea? Okay. So you might ask, why bother making the list of possible rational zeros then? Why not just graph the thing on my calculator and just use whatever I see there? Which is a reasonable response, right? Here's the reason. Are you going to be able to tell the difference between an x-intercept of 3.9 and the x-intercept of 4 by looking at the picture? Probably not. Like, those are awfully close. What if it was 3.99? You definitely probably can't then, right? And the problem is, if the x-intercept is actually 3.99 and you try 4, the synthetic division won't work. So you need that list of possible rational zeros to go, okay, I got to get everything that's close to 4. So if 3.99 was on that list, you could, okay, better check that one too, rather than just moving on from 4. Okay? In addition, you can have irrational x-intercepts. So like the square root of 2 could be an x-intercept. And that's something that would not appear on your list of possible rational zeros. The square root of 2 looks a lot like 1.5, because the square root of 2 is 1.41, yada, yada, yada. If you try synthetically dividing by 1.5, that wouldn't work. And again, you might go, well, why not? And if you looked at your possible rational zeros, you'd probably not have 1.5 on the list, and you would go, yeah, that one I know is not going to be, isn't a synthetic division candidate. So we do want that list of possible rational zeros. It does tell us a lot of information that the graph alone does not. So what we want to do is we want that list of possible rational zeros and then use the graph to identify the good candidates from that list rather than just using the graph by itself. Because it's possible you get things from the graph that are not good candidates because they're not on that list. Of course. Okay. Should we do this one more time all the way through? Okay, there's still more theorems and like weird things that can happen that we haven't touched on yet, but this is kind of the bare bones of the process. So let's do this one more time. So we're going to factor x to the fourth plus x cubed minus 8x squared minus 2x plus 12. So let's start by using our rational roots theorem to list our possible rational roots. Notice here, what's the leading coefficient? 1. The only factors of 1 are just 1. And anything divided by 1 is just itself, right? So all I'm going to get from my possible rational roots are just the factors of 12. Does everybody kind of understand how I went right to that? You'll say we did. What it boils down to is if the leading coefficient is 1, your possible rational roots are just the factors of the constant term. If the leading coefficient isn't 1, you're going to still have the factors of the constant term, but you also have another list depending on how many factors you have of that leading coefficient. Okay. Next thing I want to do is I want to look at the graph. So I'll go to the y equals, clear out what's there, and then type in my polynomial exactly as it's written here. Give you guys a second that are following along to get that typed in. All right, so now I'm going to go to the window. What should I pick as my x min? It's the smallest number from my list of my rational roots. And the biggest? Positive 12. So maybe I'll just do negative 15 to positive 15. And I'll hit graph and take a look at what I get here. So I see 4 roots, it looks like. But they're still kind of far enough away that it's hard to read exactly where things are. So I'm going to zoom in again. It looks like negative 5 is maybe here-ish, and positive 5 is over here. So that seems good enough to just do negative 5 to positive 5. Again, it doesn't really matter there. I just want to be able to see all 5 of the roots. Everybody okay with that? All right. So let's read what we have here. So let's do the negative ones first. So this is -1, that tick mark there. And that's -2. And that's -3. So I see -3. This one is probably -1.5-ish. You guys agree with that? So I'll write those 2 down, and then we'll look at the positives. Okay. So this is +1. That's +2. And this one is, again, somewhere in between 1 and 2. I don't know, maybe 1.5-ish. You guys agree there? So what I'm going to do now is I'm going to look at my list from the rational roots theorem and see which one of these graph x-intercepts match up with the things on my list. So I see -3 there. I don't see -1.5 on this list anywhere, though, or anything really kind of close to -1.5. What that tells you is that this is irrational, and that's a bad candidate to use. Same thing with +1.5. Would not want to use those to do the synthetic division. We do have +2, though. Everybody cool so far? Okay. So let's do some synthetic division now. The ones we'd want to use would be -3 or +2. It doesn't really matter which one you use. For the sake of argument, let's use -3 because I wrote it down first. There's no good reason to pick that one over the other one. So I'll just make a decision. So I get 0, which is great, right? That's what we want to have happen. Now I have 2 options here. What this division gives me is that I can factor that polynomial like this. Oops, that's a minus. So I could either try to factor this, or I can keep going with my synthetic division because I still have another excellent candidate to use. I'm going to do synthetic division again, just for something different. Everybody okay with that idea? So what I'm going to use the synthetic division on is the quotient of that previous division problem. So that worked again. So I still have the x plus 3, but now I have x minus 2, and then x squared minus 2. I wouldn't want to do synthetic division again because the other 2 x-intercepts I have are not on my rational roots list. So those are not good candidates to do any division with. I would look to see if I could factor this anymore. Can I factor this anymore? X squared minus 2? I cannot, because it's not a difference of 2 squares, because 2 is not a perfect square. So this would be as good as I could do factoring this. If I wanted to solve this, that's not what I asked you to do in this problem. But if I were to try to solve this, I would get these 4 answers. And just so you know, square root of 2 is approximately 1.41. That's the 1.5 and -1.5 we saw by looking at the graph. Hard to tell that difference between like 1.5 and the square root of 2, right? 1.5 is a perfectly reasonable rational root. That could be something we get. It wasn't in this case, but without that list of possible rational zeros, we wouldn't have known that 1.5 was a garbage thing to try. Everybody okay there? Okay. I'm going to stop here.